We're moving into planetary circulations now. So we have talked about temperatures and how solar radiation brings energy in, how it's unevenly distributed. We've learned even somehow how energy moves throughout our atmosphere. We've talked about pressure. We've talked about density. We've got into a discussion on winds here this last week now. And we've even talked about how precipitation occurs, how moisture changes states in the atmosphere from gas to liquid to solid. But what are we going to talk about now? Well, we're going to put it all together and talk a little bit about planetary circulations. What do I mean by a planetary circulation? Well, what I'm looking at is the Earth is a globe, and what happens in one part of the world in the atmosphere impacts another. We've said the atmosphere is a fluid. So if I disturb one part of a fluid somewhere, it's going to impact another part. And if you look at it as a whole, we can discover that there's a general circulation to the Earth. So let's explore that a little bit here. So what are some of the principal features of this? Why is it important? Well, if the Earth didn't rotate, we'd have one side that got really, really hot, and one side that got really, really cold. And we would have air going up where it's hot. We've learned convection occurs where it's warm. So we'd have the air going up, sinking where it got cold. The Earth rotates, so changes up a little bit. With that, what happens is we have three belts really to look at in the atmosphere. Along the equator and just north of it, we have easterlies. And those easterlies flow into the equator. And then just north of that, we have the westerlies where we live. You'll notice along 30 degrees north, we have wind blowing to the southwest, wind blowing to the northeast. Well, right in here, you have divergence, right? Well, actually, you get big high pressures right along 30 degrees north. And along the tropics, where these winds come together, you actually have a belt of lower pressure, the intertropical convergence zone. And finally, around 60 degrees north or so, we have a bunch of low pressures that typically reside in that area and move along. So you can see, if you were to look at an idealized circulation, we have a couple areas of high pressure, a couple areas of low pressure, and winds flowing in different directions depending on which latitude they're at. We live in the westerlies, almost all of us, so our winds are generally coming out of the west. If we were down in the tropics, they'd be generally coming out of the east. So here are the high and low pressures, as we've just discussed and seen how they form because of the general wind patterns. And if you look at, this is an average picture of lows and highs. So in January, you notice the highs are pushed a little bit south, lows pushed a little bit south in the northern hemisphere. Well, why is that? Well, it is because the sun has moved further south, so we push everything to the south. We have more intense lows, bigger temperature contrast. Highs are a little bit weaker. And here is your intertropical convergence zone right down in this area, probably just a little bit of south of the equator. And notice a big high over Siberia here, high pressure generally across Canada and stuff here. Now in the summertime, what happens? Well, everything moves north, our summertime, not the southern hemispheres. I want to deal with northern hemisphere where we live. And all of a sudden you went from high pressure over Siberia to low pressure. And the high that was the central Atlantic or southern Atlantic has now moved into northern, off of the Bermuda high is what we usually call it, because it's right all across Bermuda area. So you can see everything we've talked about. High pressure belts, low pressure belts, they move north and south with the sun, but they're still there generally. Yes, there are features that flow through that and disrupt it at times. So we've looked at this. Think about this now as well. Here's another interesting fact. Major deserts are all located on the eastern flanks of these Bermuda highs, or highs at 30 north. Why is that? Well, the air tends to sink on the eastern flanks. Think about it. If you lived in the Carolinas, Florida, you're on the western side of the Bermuda High. You get lots of rain, don't you? And that rain comes because it's right on the edge of where the sinking is, but it's also got some vertical motion because you're getting some high pressure some low pressure to the west and stuff, fronts moving into that area. So you wind up with storms there. On the other side, you have the Saharan Desert. If you were down around Chile, which is another on the eastern side of it, we have another big desert. So on the eastern flanks of these major highs, we have deserts. Now, when you look up in the poles, you have over the North, Aleutian Low over the North Pacific, Icelandic Low. Southern Hemisphere is a big area of circumpolar vortex, and in between there, we have fronts that move up and down. And we've had enough fronts go through us in the last winter to last for me for quite a while. And I had one last week, but they move out of the Arctic or the north and come back to the north. The polar vortex, it's upper level, circumpolar. It sits there all winter long and gradually dissipates in the summer. The stronger it is, the less cold air can move south. Winds are blowing very hard around it. Weaker it gets, the better chance of that Arctic air moving south. And here you can see winds blowing from west to east in the mid-latitudes where we live. And with that, we know that over the tropics, sun's almost always overhead, really hot down there all the time. Matter of fact, it's an interesting fact. The temperature has never got below 60 degrees in Puerto Rico. So think about that up here, where how cold we get. Even in Florida, temperatures have gone below freezing all the way down almost to Key West. So here, not that far south, a little way south of that, we're in the tropics. We don't even get below 60 degrees. Further north, almost always is staying cold. So the tropos pauses well low. We live in the westerly band, mid-latitudes. The tropopause will go up and down a lot, depending on weather. So with the trade winds, the winds coming out from the east, down just north of the equator, what you wind up with is a lot of sinking motion. And just off the surface, you wind up with a layer of not much moisture coming in. So you get this marine layer here, which can keep clouds out of that area. A lot of times, way back in history, when ships used to come across from Spain or France or England to the United States, a lot of them would try to get in those easterlies because it allowed the flow, pulled the ships here. But if they got a little bit too far north, they get what they call the doldrums. And what do you wind up with in the doldrums is not much wind. So they wound up not being able to move. And with the sinking motion, the dry air, sometimes they really had a lot of problems with water and all. So the intertropical convergence zone follows the sun. I want you to look at this map a minute because you may get a question about this map in your studies this week. Notice over the oceans, it doesn't move a whole lot. Why is that? Well, it takes a lot of heat to warm up water. I mean, you think about it. The sun shines and shines and the water temperature slowly seems to go up. I know I live fairly close to the coast, and during the wintertime, my water temperatures drop into the 40s. By March, I'm starting to usually get pretty good sunshine. You know, the sun's now moved north of the equator, right? It's coming up towards me, but I don't get my warmest water temperatures until July or August, after the sun has reached its peak up here. It's take that long to warm it up. And then I'm in the 70s many times, or maybe even the low 80s. So you see, it takes a long time for the water temperature to warm. In the wintertime, it takes a long time for it to cool. I don't get my coldest water temperatures till January, or maybe even early February. Now, over land, very different. Land heats up very quickly. So you push everything very far north with all these continents here in the summertime. And then it gets down over the water. Well, not so fast here. So continents make a big difference because they can heat up quicker and cool off quicker. What that happens then, you'll notice that I told you a while ago there was big high pressure in the wintertime over Asia. Well, if you have high pressure over Asia, you're getting a lot of air coming out of the Siberia and pushing down away from there, pushing all that dry, cold air into India, into Cambodia, Thailand, Vietnam. And then when you get to the summer, the intertropical convergence zone moves back north of you. You switch to low pressure, literally. What happens? All that Indian Ocean moisture comes back up and into that area. So you get lots of rain. And it's consistent. Once it sets in, it stays there. And it's consistent in winter. That's why it's called a monsoon. The winds stay there for a long time, months. Interestingly, we can be some areas on the edge of these as well. San Diego, on the eastern side of the Pacific High, notice, gets almost no rain May through September. Very little, if ever. Then in the wintertime, it gets a little bit more because by that time, the high shifted south and it gets into the westerlies. Charleston, on the other hand, on the western side of that high pressure, the Bermuda High, what's it get? The most rain in the summertime. It continues to get rain during the winter because it's in the westerlies, but has much more rain in the summer. All these are global patterns. And with that, the fact that they stay there for so long, they impact the oceans. The ocean water moves because the wind pushes it. So if the wind's pushing it, you wind up with the Gulf Stream coming out here, moving along the west coast, all of this around the North Atlantic gyre. Matter of fact, that Gulf Stream continues on over to England. It allows England to be warmer than it normally would be. Notice the California current along California coming out of the north. It keeps the water temperature cold there all year long. We have a monsoon also called North American monsoon. It occurs over the western part of the United States, basically Arizona, New Mexico, maybe into Utah or Colorado at times, particularly over Mexico. If you were to look at Mexico down here, you would find it's pretty high. Elevations get up fairly high and it's fairly flat. So what happens is sun heats that area really well. So with that heating, you get lots of rising air. Well, we know that when rising air occurs, we're going to pull in air from somewhere else. Where does it pull it in from? It pulls it in from the Gulf and from the Pacific, Southeast Pacific. All that is moist air, warm air. So it's being pulled into there and then lifted up to the north. Also, we have learned from our pressure days when we talked about pressure that when the air gets hot, pressure doesn't change into vertical very fast. So what you wind up with is big high pressure aloft and low pressure at the surface down here. Rossby waves are long waves in the atmosphere, and we're going to look at those in a little bit more detail here in a couple minutes. Here you can see what they call zonal flow. It moves from west to east fairly quickly, little bits of a wave pattern to it. And meridional, which we've had a lot of lately, very deep waves, pulls up a lot of moisture and warm air out ahead of it, and behind it, lots of cold air. We've had lots of those this spring here. Here's their blocking patterns. Think about it if you ever look at a stream and you'll just see sometimes this circle flowing around and around in one area. not moving. The water just, you put a log in it, you just see the log just go around and around in the same spot for a while. That's what happens when we get a blocking pattern in the atmosphere. So what these do is they cause a lot of either rain or cold, maybe dry. They're going to bring extremes because they're persistent. They stay over an area for a long time. It's actually one of the things meteorologists look for, is to see if a blocking pattern is going to set up, because if it is, we may be dealing with significant bad weather of some type. Here you can see blocking patterns set up over the Midwest in 1993. It produced a tremendous amount of rainfall in the spring and early summer. So much so, there was some record flooding on the Mississippi River. And because of it, you have big high pressure here over the southeast United States. Well, what happened? They didn't get much rain at all. And here you can see how much fell. Way, way, way above normal. Over 300% more than normal. Jet streams. Why do they occur so far up in the atmosphere? Why not just occur down at the surface, right? Well, part of it's friction, as we've learned, but part of it is the fact you think about right before the tropopause is where there's the greatest temperature change in the atmosphere. So where that temperature change is, that means there's very low pressure, where air is warming up there, or spread apart with high pressure. So you wind up a very strong gradient due to temperature. And that gradient causes these extreme winds that you get aloft. So, and around the poles and all is where the jet streaks develop. And they shift. In the summertime, the main jet stream is further north. In the wintertime, the main jet stream is further south. And because we'll talk about Rossby waves later, let's look at these a little bit later as well. And we're going to see little ripples of low pressure. We call them short waves because they're not as long or big as a Rossby wave. With that, they produce vertical motions. They can produce sinking and cause high, or produce lift, divergence aloft, and cause low. Another package here is El Nino, La Nina. El Nino refers to the Pacific Ocean temperature change. We're going to look at that a minute also. I want to just go through a couple of these extra slides here. One of the things with global circulations, because they last a long time, they pull the ocean currents around in such a way. So with the Gulf Stream along the east coast of the United States, I generally have a flow of the Gulf Stream to the north, just off the coast. And if you're out in the ocean, sometimes in the summer, off of Myrtle Beach or off the Outer Banks, you'll feel the water can really get picked up moving that way, especially if the Bermuda High gets strong and it gets a very strong southerly fetch to it. Now, what happens? Well, we know the Coriolis force, it doesn't just act on air, it acts on water. So it will want to pull that water to the right. If it pulls it to the right, it's gradually going to, the deeper it goes, it's going to gradually, literally turn the water into a whole circle at the way it's motion, just depending on how deep it goes down. I have had this happen when I've been to Myrtle Beach, or when I've been even to Daytona Beach one year. What happens is the water pulls out to the right. Gradually, as you get depth, it comes back from low elevations in the ocean, lifted back up by the coast, and you wind up with extreme temperature changes. And what happened to me was it was 80-degree water temperature one day at Daytona Beach. The next day it was in the 50s, all because of the X-Men spiral. We'll talk a little bit more about El Nino and all of its phases here as we go through. There's a North Atlantic oscillation, which we'll try to show you a little bit too on that. It has an impact, especially in the winter. When we get positive index, we tend to get stronger than usual winter winds blowing across the North Atlantic. All the North Atlantic oscillation is we look at a pressure difference between somewhere where typically the Bermuda High would be sitting and up over Iceland. The greater the difference, the more positive that index is. The less that difference, the more lower that index is. And these help to steer the winds across the United States. And here you can see it. And the jet stream can get, when it's positive, it tends to be colder than normal, but you can also really get some really good storms and all that develop when it's negative. And one of the interesting things is trying to forecast. This can hang on for weeks at a time. So knowing that, it's interesting to try to figure it out ahead of time before winter occurs. We don't do a real good job with that, unfortunately. I want you to notice 1960s. I grew up in the 60s. And you'll notice the NAO was almost always negative in the 60s. And I can remember growing up in Pennsylvania having all this snow. By the 70s, it went away. Why that happened? Because the NAO switched. It became more of a positive phenomenon for much of the time. And some of our warmest winters are going to be positive NAOs, interestingly. The Arctic oscillation, all that refers to is how strong the polar vortex is. And the polar vortex can be really strong sometimes. If it's really strong, you wind up getting nothing out of Canada or out of the Arctic coming into the United States. So actually, I'm rooting for a very strong Arctic oscillation because I don't like that cold air. So, and then we have Pacific. It's another phase, another one you work with. All right, Madden-Julian oscillation is the last thing we're going to touch on this. Interestingly, there are areas of thunderstorms that develop over the Indian Ocean and around Australia and migrate slowly to the east. They move at about 9 to 18 miles an hour. They form in the tropics, but they impact large areas of the atmosphere all the way up into the mid-latitudes. As they move around, they tend to enhance the rainfall coming into the west coast of the United States. As they come east, depending on whether it's an upward phase or a downward phase, they may help to trigger a stronger storm, extratropical storm that we're going to talk about next week more. So the MJO is a major impact on our weather. We've just really learned about these in the last 15 to 20 years and got a lot better understanding of how they work and how they can interact with the winds aloft and all. They typically, really these oceans of art and rivers and stuff of moisture that come in on the west coast impact that. So with that, I really wanted to show you real time and then what's going on with ENSO or El Nino. Well, right now we have La Nina. You can look at SSTs here, anomalies. How much below normal or above normal? Notice to the left here is 0, which is normal. Here's -5, -1. You'll notice Nino 3.4 is the region we typically use to determine what we have in an El Nino or a La Nina. And right now it's been negative for a while, not real far, but really dropped off here December to January into February. Now it's trending back to being a positive almost. So we actually were in a La Nina for a relatively short time, December, January, February. Now we're trending back to normal. You can get forecast of this. What does that mean? Well, if you have a La Nina, it typically means the winds from the west aren't going to be as strong. They're going to be more wavy. So that would tend to bring more cold air into the United States, potentially not as much rain onto the west coast of the United States. If you have El Nino, we tend to have stronger winds and more rainfall on the west coast. Finally, I just wanted to show you as well here. This is a current weather map, forecast model weather map. We talked about Rossby waves. Rossby waves are long, long waves. Here is a big Rossby wave. It just sits in this area and impacts all of the central United States almost to the East Coast. We have another Rossby wave that's out here off the west coast of the United States and another one over Greenland. There's about 3 of them in the east in our part of the world right now. And if you were to watch the flow through these Rossby waves, I talk about short waves. Take a look. Here's a little tiny trough in the atmosphere running through the Rossby wave. Here's another one running through the Rossby wave. It gets deeper when it gets into the middle of Rossby wave. It weakens as it goes out. So you can actually see these. I'm going to loop this here. And you can actually watch them move through the flow and then up and over us. And the Rossby wave doesn't move a whole lot. It just sits up here in Canada or sits out the west coast of the United States or the east coast of Greenland. So while the Rossby waves don't move, these other ones do move across, move out of the Rossby wave and in. Now, I talked about blocking patterns. You'll notice there's a big high sitting right here. Counterclockwise flow around it. Notice this short wave dropped in and sits there. It's not moving, is it? That's the block I've been talking about. It can occur anywhere in the world. And this is a blocking pattern that's occurring over that part of the Atlantic right now. If you were in a cruise ship, you might hate to be out in here because it's probably bad weather going into this area around Bermuda and all. So this is all about the planetary circulations. I hope you got a little bit out of this. I know I probably went long, but if you have any questions, let me know.